The overarching conviction among most researchers is the Big Bang theory, which remains the primary explanation for the origins of the universe. This theory encompasses the creation of stars, planets, and all life on those planets, including ourselves. Despite its rather unconventional name, the Big Bang offers a clear view into what could have happened. At first, the universe was condensed into a brief space smaller than a pinhead, with particles densely packed. From this tiny point, a massive explosion of matter and energy occurred, known as the Big Bang. This event, happening billions of years ago, set the stage for the unfolding of cosmic history. However, advancements in scientific knowledge have led to increasing inconsistencies with the predictions of the Big Bang theory. When NASA launched the James Webb Space Telescope, JWST, the largest and most advanced space science observatory ever developed, scientists speculated that its observations would support the theory of how the universe came to be. Surprisingly, after only 1 year in space, the telescope astonished researchers with its unprecedented ability to peer deep into the universe's past. The JWST's groundbreaking capabilities have revealed galaxies dating back to a period so ancient that it challenges our understanding of the universe's beginnings. This discovery has sparked an intense investigation into what existed before the Big Bang. One pivotal moment in this mission occurred when astronomer Rohan Naidu, working with data from the telescope, stumbled upon a galaxy dating back to just a short time after the Big Bang, making it the oldest galaxy ever observed. Naidu's discovery sent shockwaves through the scientific community, highlighting the transformative potential of the James Webb Telescope. Its mission to revolutionize our understanding of the universe has only begun, promising to unveil extraordinary insights into the earliest chapters of the universe's existence. This uncharted territory holds the key to understanding the formation of the first stars and galaxies. The telescope's findings have defied initial expectations, uncovering galaxies with characteristics surpassing previous predictions. This unexpected abundance of early galaxies has ignited a flurry of scientific inquiry, challenging researchers to reconcile these observations with existing theories. As scientists grapple with these revelations, they face profound questions concerning the fundamental nature of the universe and the forces shaping its development. Moreover, the James Webb Telescope's technology is revolutionary. Positioned 1.5 million kilometers away from Earth, shielded from terrestrial interference and cooled near absolute zero by its tennis court-sized sunshield, the telescope features a giant segmented mirror and exquisitely sensitive instruments designed to uncover details of cosmic dawn previously unseen. This epoch, known as cosmic dawn, occurred no more than a few 100 million years after the Big Bang, marking the period when the first stars and galaxies began to form. The process of how this unfolded remains a subject of intense study, with theories ranging from the effects of dark matter and dark energy to the interactions among starlight, gas, and dust. The telescope's observations of galaxies from cosmic dawn present a unique opportunity for astronomers to test their understanding of these underlying phenomena. By examining these ancient galaxies, scientists can either confirm the validity of their current models or identify gaps in knowledge that could lead to major new discoveries. Initially, it was projected that the telescope would find only a few faint and small galaxies in its pilot observations. However, reality has far exceeded these expectations. The telescope's very first images of the distant universe revealed numerous galaxies with ages, sizes, and luminosities that surpassed all predictions. This unexpected abundance of early galaxies has triggered a race among astronomers to claim new records for the earliest known galaxies. Each day brings claims of another record-breaking discovery, leaving the scientific community in awe and prompting a reevaluation of our understanding of cosmic history. In the wake of the James Webb Telescope's findings, theorists and observers have scrambled to account for the existence of these surprisingly mature early galaxies. Some speculate that flaws in the analysis of the telescope's initial observations may be responsible for these anomalous findings. However, the consensus remains that these discoveries represent a paradigm shift in our understanding of the early universe and offer tantalizing clues about the nature of cosmic evolution. The recent discoveries from the James Webb Space Telescope regarding early galaxies raise significant questions about the nature of the universe and challenge the assumptions of standard cosmological models. While some scientists speculate whether these observations can be reconciled with existing theories, others suggest that they might be the first indications that the universe is even more complex and peculiar than previously imagined. At stake is nothing less than our fundamental understanding of how the structured universe we know emerged from primordial chaos. The early findings of the JWST have the potential to rewrite the opening chapters of cosmic history, shedding light not only on distant galaxies and faraway cosmic phenomena, but also on the very existence of our own Milky Way galaxy. As Mark McCaffrey, Senior Advisor for Science and Exploration at the European Space Agency aptly puts it, "You build these machines not to confirm the paradigm, but to break it. You just don't know how it will break." The origins of the JWST can be traced back to the Space Telescope Science Institute in 1985, even before the Hubble Space Telescope was launched. At that time, Garth Illingworth, then Deputy Director of STSCI, was tasked with imagining what would come after Hubble. Despite initial reservations, Illingworth and a small team began laying the groundwork for what would eventually become the next-generation space telescope, later renamed JWST after a former NASA administrator. Unlike Hubble, which primarily observes visible light, JWST was designed to see in the infrared spectrum, allowing it to peer much deeper into the universe. This capability is essential for studying early galaxies, whose light has been stretched into the infrared due to the expansion of the universe, making them invisible to telescopes like Hubble. With its large and cold star-like mirror, JWST became the perfect tool for unlocking the secrets of cosmic dawn. The need for JWST was underscored in 1995 when the Hubble Deep Field Observation revealed a plethora of galaxies in what was thought to be an empty patch of sky. This discovery hinted at the richness of the early universe and reinforced the importance of a telescope capable of delving even deeper into cosmic history. After over 2 decades of development and at a cost of around $10 billion, JWST was finally launched on Christmas Day in 2021. By July 2022, it was ready to begin its first year of scientific observations. Early programs like the Cosmic Evolution Early Release Science Survey and the Gravitational Lensing Advanced Survey from Space were specifically designed to search for early galaxies. While initial expectations were modest, the outcomes far surpassed forecasts. The JWST observations have challenged existing thoughts about the early universe, revealing galaxies that defy conventional models. These unforeseen discoveries highlight the significance of pushing the limits of scientific exploration and showcase the extraordinary potential of cutting-edge advancements like the James Webb Space Telescope. As researchers continue to unravel the mysteries of the universe, they are poised to transform our understanding of cosmic history and the forces that have shaped our universe into what we see today. The early observations made by the James Webb Space Telescope have bewildered astronomers by uncovering incredibly distant galaxies almost immediately. Before JWST, the most distant known galaxy was GN-Z11, discovered in 2015 with a redshift of 11, corresponding to a cosmic time of around 400 million years. However, from the start of JWST observations, the GLASS team, led by Rohan Naidu, and another independent group made a remarkable discovery. They identified a galaxy named GLASS Z13 at a redshift of 13, approximately 70 million years earlier in cosmic history than GN-Z11. The rapid pace of these discoveries was facilitated by simplified methods for estimating redshift, which, while less precise than direct measurements, provide a quick assessment of a galaxy's distance. Surprisingly, GLASS Z13 appeared unexpectedly bright and massive, already containing a stellar mass equivalent to billions of suns, despite being significantly younger than the Milky Way. Subsequent observations revealed even more astonishing findings. Many galaxy candidates with estimated redshifts as high as 20 emerged, indicating their existence a mere 180 million years after the Big Bang. Some of these galaxies exhibited disk-like structures, a feature not expected to appear so early in cosmic history. Furthermore, evidence emerged for galaxies comparable in size to the Milky Way at a redshift of 10, less than 500 million years after the Big Bang. These rapid developments challenge the predictions of the standard cosmological model Lambda Cold Dark Matter, Lambda CDM, which describes the universe's evolution based on our understanding of dark energy and dark matter. According to this model, galaxies of such size and luminosity shouldn't have formed so early in cosmic history. The emergence of massive galaxies in the early universe presents a significant puzzle for cosmologists to grasp. To understand this conundrum, it is essential to comprehend the early stages of the universe's formation. In the first seconds after the Big Bang, the universe was a hot and dense soup of primordial particles. Over millions of years, the first stars began to form, creating the building blocks for galaxies. This process of cosmic evolution, from chaotic beginnings to the structured universe we observe today, is thought to have taken roughly 1 billion years. JWST observations have challenged this timeline by revealing galaxies that appear too mature for their cosmic age. Instead of observing various small protogalactic fragments merging to form larger galaxies, as predicted by current models, JWST has identified galaxies that are already sizable and luminous. Follow-up observations with instruments like the Atacama Large Millimeter Array, ALMA, in Chile have provided additional evidence supporting the authenticity of these distant galaxies, ruling out the possibility of low-redshift interlopers. These remarkable discoveries open new avenues for understanding the early universe and may require revisions to our current cosmological models. JWST continues to revolutionize our comprehension of cosmic history, challenging our assumptions and pushing the boundaries of astronomical exploration. The absence of visible dust in the observations made by the Atacama Large Millimeter Array highlights the challenges faced by telescopes in confirming observations made by the advanced capabilities of the James Webb Space Telescope. As Rohan Naidu noted, while JWST can follow up on its own observations, ALMA's difficulty in detecting the galaxy underscores the complexities of confirming such discoveries. The implications of JWST observations are profound, potentially challenging the canonical Lambda CDM cosmological model and requiring modifications. Michael Boylan-Colchin expressed surprise at the results, suggesting a significant departure from our current understanding of cosmology. One controversial theory that could explain these findings is modified Newtonian dynamics, MOND, which challenges the existence of dark matter and proposes alternative explanations for observed gravitational effects. JWST observations aligning with MOND expectations intrigue proponents like Mark McCaffrian, who sees this as further evidence supporting the theory. However, skepticism remains among some researchers, such as Jiahao Chun, who highlight the difficulties in reconciling MOND with existing data. On the other hand, the absence of dust in early galaxies could offer a simpler explanation for their brightness, potentially complicating efforts to accurately measure their masses. Andrea Ferrara suggests that dust may not have had sufficient time to form in the early universe, or may have been expelled during galaxy formation. Charlotte Mason and her colleagues suggested that JWST might be primarily detecting the brightest young galaxies, which are easier to detect. David Spergel proposes that efficient high-mass star formation in the early universe could explain the observed brightness of these galaxies. He speculates that early magnetic fields may have played a role in jump-starting star formation, offering a potential explanation for the rapid growth of galaxies in the early universe. The rapid influx of scientific papers stemming from JWST's initial observations highlights the significance of these findings and the profound implications they hold for our understanding of cosmology. As researchers continue to analyze JWST data, they may uncover further insights that challenge and expand our understanding of the universe. When the first data began streaming down from the James Webb Space Telescope, cosmologists were eagerly anticipating the results. Many had been working on their data analysis pipelines for years in preparation. Rather than following the traditional peer review process, which can often take months, astronomers chose to publish their findings on AR14, a site where scientific papers can be uploaded after minimal review by referees. This approach allowed a new form of peer review to unfold in near real time on platforms like Twitter and other social media channels. Rohan Naidu describes it as science by announcement, and the resulting flurry of discussion was intense and unprecedented. Nancy Levinson, the interim director of the Space Telescope Science Institute (STSCI), admits underestimating the magnitude of the activity. However, there are concerns about the potential downsides of this rapid dissemination of findings. Klaus Pontoppidan, JWST project scientist at SDSCI, noted that while the quick sharing of results allows for rapid publicization and discussion, there's a risk of rushing the process.